All right, second video on Descartes' rule of signs. I got this new function, f of x equals 2x to the fourth plus 11x cubed minus 17x squared minus 86x plus 120. All right, so I'm using Descartes' rule of signs. I noticed that there are two sign changes over there. This tells me that there are either going to be two positives or zero positives. And then I plug in the negative x over here, and then I get this, and I find out that there are three sign changes, which means I'm going to have, my mistake. There are not three sign changes. I made a big old oopsie right there. That big eraser's too big. This actually is not a sign change, positive. So we either have 2 or 0. So I go ahead and I set up my table, and it's degree 4. So the degree of the polynomial is 4 right there. So I look at that. All of my answers have to come out to 4. And there were two reals that are positive, which are two reals that are negative. There would be no complex. Two reals that are positive, no reals that are negative, which means there would be two complex, zero positives, two negatives, and two complex, or none, and four complex. All of the answers are going to be complex. So that's Descartes' rule of signs in a nutshell. Now, not the fundamental theorem, sorry, the rational root theorem. Okay, so the rational root theorem, and this is what the next thing is going to be on, it states that if rational roots exist. We're not talking about real roots. We're talking about a specific type of real root. If a rational root exists, it's going to be determined based off that 120 and the 2. The lead coefficient, the 2, and the ending coefficient, the 120 over there. So based upon that, the constant term, I should say, based upon that, we can break down what possible rational roots exist. So we take the 120 and we factor the crap out of it. So we're going to take the 120 and factor it. Now, when I factor, I always factor in pairs. I start off by 1. 1 times 120. Then I go divide by 2. It does divide by 2 to 60, 3 to 40, 4 to 30, 5 to 24, 6 to 20, 8 to 15, 10 to 12. And the only number after 10 would be 11, and 11 times nothing gives us 120. And you'll notice that it just wraps around, which is why I like to write them in pairs. It's a personal preference. Next, we focus on the front number. The front number was 2. There's only one factor, 1 times 2. What you're going to do next is you're going to take all those green numbers and divide them by the red numbers. Now, when you divide all the green numbers by 1, you get that set. 1, 2, 3, 4, 5, 6, 7, all the way to 120. But then when you divide them by 2, these are the only ones that are unique. What I mean by that is when you divide something like 8 by 2, what you end up getting is a number that is already existing within your set. So you don't need to talk about that one. All you care about are the unique ones. Those are unique, and these ones by themselves. So these are all the possible rational roots if a rational root exists. So if rational roots exist, they're going to be these guys. So now you just have to find out which ones actually work. Now the rational root theorem, in addition to that, the rational root theorem, if one of these is a rational root, then that means when you divide, the remainder is going to be 0. Okay. Now, this video doesn't really have to do with the rational root theorem or even have to do with Descartes' rule of signs. I wanted to talk about a corollary that has to do with Descartes' rule of signs. And this has to do with the upper bound and lower bound limits. Excuse me. So what we're going to do now is we're going to take some of these and we're going to divide it from this function right here. I picked some out just so you could see it. So we know that these are all the possible roots that can exist. What I decided to do is I decided to test 4. So I tested 4 and I did long division on it. So when I dropped down, I did it, I multiplied, so 4 times 2 is 8. That's where this 8 comes from over here. And then 8 and 11 add up to 19. Then I multiply the 4 and the 19, I got 76, combine the 76 with negative 17, and got 59. And you can see how this is going to work out. Now, what you guys should notice is that all of them were positive down here. All of these numbers right here are positive, okay? If that ever happens, you now know that the number you divided by is an upper bound, all right? So if you divide by a positive number, and the result on the bottom row is all positive values, that number is an upper bound. That means there are no roots bigger than the number that you divided by. So now when you're taking a look at these numbers, you don't have to try any of these roots here because 4 was the upper bound. There was nothing there. This is why Descartes' rule corollary is actually really, really useful, is sometimes it limits what you have to test. You don't have to test numbers larger than 4. Now, unfortunately, you don't know that until you test a number, right? Like you wouldn't have known that unless you tested 4, but if it was to happen, it would kind of tell you, stop testing numbers bigger than that. You don't have to test anything. You should start testing some of the negative values or numbers that are less than that. Now, the second part to Descartes' rule of signs is that if you try to divide by a negative value, that negative value, like -8, can give you things that alternate in signs. So you'll notice you go from 2 to -5 to 23. So you go positive, negative, positive, negative, positive. And that right there, alternating signs, is the second part to Descartes' corollary. What this tells you is if you're trying to test a negative number, then that negative number, when the signs alternate on that bottom row, that is now a lower bound. Now, why is this so important? Well, remember the numbers that I gave you up here. Those are the possible rational roots. Those are the possible real numbers. Possible rational numbers, not real numbers, because you can also have the irrationals. But these are the possible rational numbers. So now, if you took all those rational numbers and listed them out, this would be the entire list of numbers right here. But using Descartes' lower bound and upper bound theorems, or corollaries, you have now been able to eliminate all of these because -8 is a lower bound. And you were able to eliminate all of these because +4 was an upper bound. This tells you that if there are roots, they're going to happen right in there in that green sweet spot. So all those pink values can't work because the -8 was a lower bound, and all of the blue numbers can't work because +4 was an upper bound using Descartes' corollary. All right. If you have any questions, hit me up. Once again, you're not solving anything. This is more of an analysis. So you're doing an analysis on the function and understanding what's going on here. Doesn't make a whole, it doesn't feel like you're doing much. It's really important when you have larger degreed polynomials. It kind of narrows the scope of what you should be looking for. All right. If you have questions, please hit me up and I'll talk to you guys later.